Okay, so let's remember what was going on recently. I think I will start with this ever-growing homework of the last lecture, which was this one. So remember, the idea was that when you're learning something like category theory or topology that has a rich language and you understand new concepts, and you have a lot of examples of topological spaces, or in this case of categories, it's a very good practice to try to, for every new category, let's say that you find out, okay, here's a category, you test all those concepts that you have learned so far and answer the following question, like, does this category has this kind of object? Do I already know this kind of thing, maybe with a different name? In case of constructions like this one, like sums and products, are they guaranteed? Okay, how do we call them? In case of like mono and epi, maybe the arrows have a special name in a category that I already know. We have seen that this is always guaranteed. Okay, my pen has a problem. We have seen that this direction is always guaranteed. If it's split mono, then it's mono. But the other direction is not guaranteed, so immediately you have a good question to ask in each category. Does this hold, I mean this one, does this hold in, I don't know, in this category, in this category? In this way you have like free exercises to practice. So here, like what I did was like, the idea is that this is full of homework, right? And I have given some answers that we have met together, and I would like to maybe to focus in one or two. So for example, we have met that there is an initial object in the category of sets and functions, and this is the empty set. We know that there are many terminal objects, which are, any singleton is a terminal object. We have found out that in the category of sets, sums are guaranteed, and they are given by, for example, the disjoint union, one disjoint union, because you can implement it in any way you like. I mean, not any way you like, but you can implement it various ways. And in products, like it's the Cartesian product, and so on and so forth. So, like, I think we had given this answer as well to group if there is an initial element in the category, initial object in the category of groups. The first candidate maybe would be to say, okay, the category of groups, it looks a bit like the category of sets, so maybe I'll try the empty group. What is the problem with this approach? Somebody please help me. Yes? Well, if your set is empty, there are not many ways that you can define a binary operation on it. It will necessarily be the empty one, let's say. But there is an objection, Harati. What? There's no such thing as the empty group. One of the, remember, a group is something together with three things, and one of them, its type is that it's an element of the G, of the group, it's a constant. So there's no such thing as an empty group, okay. But even if it was, I mean, it would not be guaranteed that it would satisfy what it needs to satisfy. So, any ideas? Like, what would be an initial, let's remember what it means to be an initial object. It means that this object can see all other objects, right? Yes? What you mean is like a singleton group, right? A group that's only has the identity. So it looks like this, okay? And yes, okay, so we have, no, it's not semi-group, sorry. Answering a different question, which is which one? Which is this one. Okay, so here you would have like this. Can you see what I'm writing? Not, okay. Okay, what about terminal objects? What does it mean, a terminal object? It means that every object can see you, right? You can get inside this object by any other object. Do we have a group like that? What are the arrows here? Homomorphisms, yes, okay. Group homomorphisms. So is there a group that guarantees that from any other group you can find a homomorphism to this group? Yes?
Is it every group? So you can just send anything to the unit?
I think what you're thinking is the correct answer, but what you said technically is not the correct answer. So you're saying that every group is a terminal object? Okay, sorry, when I reminded you the definition, I forgot a part. You're right. What's the part that I forgot? Exactly. Sorry. Yes. So there's a unique way to get inside any group, from every group to get inside this supposedly terminal group, if it exists. Because Manolis is right. In the category of groups, if you have any two groups, it's guaranteed that they see each other. What is it's called the trivial, I think, homomorphism. Like, send every element of one group to the identity. There is no way you can break a law. An homomorphism law, so it's a homomorphism, so yeah. And the other way around. So every group, every object in this category can see any other object, including itself. I use C as a metaphor if there is an arrow from one to another. So any ideas for a terminal object? Yes?
Same thing.
The same thing, yes. Okay. So it's a good opportunity to give it a name when this happens. So in the category of group, we have something, maybe you think it's weird, but it's not so rare and it's not so weird, that the same object satisfies the condition of being a terminal object and the condition of being an initial object. In this case, we can, it has a name, we can call it a zero, a null, or I will write here, okay. We can call it zero, null, or a bi-terminator, or maybe some other names as well. The reason I don't really like the name zero is that we kind of think of zero as an initial element and one as as a terminal element. So yeah, if you call it zero, if you say it's a zero element, it might not be just initial, it has to be also a terminal object. So what is, okay, so I'm trying to show you how you're supposed to invent your own homework here. So okay, we have this concept of a zero object. Now an obvious question to do is, okay, if I'm in a category and in it there is such a thing as a zero object, what is maybe a consequence of this thing? Like, can anybody guess and state, aha, if I know that in a category I have a zero object, such and such thing follows? Yes? Well, say it again. I don't know, it's a hearing problem. I couldn't hear you. You mean as if it's the empty set, the whole category? Like, you mean it has no objects? No. What do you mean? We already know, wait a bit, that in this category, there's no such thing. Because the only initial element is the empty set, and it does not satisfy the condition to be a terminal object. And similarly, the only terminal objects are singletons, and this is not a terminal object. So in particular, in this category, there's no such thing as a null object by terminator. We'll avoid a bit the zero terminology. That's the definition. So like it's called a zero object if it's simultaneously an initial and a terminal object. So the question is, let's say you find out you're in a category that, aha, here I have a zero object. What kind of consequences this may have? Lazarus?
All objects of the category must be connected with another.
Yes, okay. So, and how do we prove this? Lazarus has this idea, like, give me any object A and B. By the fact that there is a zero by terminator null, I don't know, object, how will you get, so like the challenge is to go from A to B. So why is it guaranteed that you can go from A to B?
Because you have the by terminal, so you can always go to the
to the terminal, like you will use the fact that Z is a terminal so that you have a way, and this is unique, okay? And you can use this thing, and this is also unique, to go to B, which means you gain the composition of these things, and you can, A can see B, and everybody can see anybody. Is this unique, the arrow from A to B? Yes? Not necessarily. And we have a good example, like in groups, we don't have only one, we may have more than one homomorphism between groups. Yes? Exactly for the same reason, we can go from B to A, but now we will use the fact that Z is a terminal object with B, so we get this arrow, and we'll use that Z is an initial object with A, and we get this arrow. These arrows are unique, but the composition may be one of many arrows. Okay. One last thing, just to warm up. Okay, what about rings? Initial, okay, I'm doing your homework here, and this is the last one I'll do. What about rings? So like, is there initial or a terminal ring? Ring is an example of something that, depending on which book you will open, you will see a different kind of definition maybe. When I say rings here, I mean with unit and not necessarily commutative. If I get rid of the identity, the unit condition, the idea is that you delete the I, so you call them ring. I don't know if you've seen this term, but it's become quite popular. And there are also rigs, which is if you forget the inverse of the additive thing. I'm sorry, N is for negation, I think. Anyway, but I'm not talking about rigs, I'm not talking about rings, I'm talking about rings. Okay, so I'm told here to give you some time to think. What is, does anyone have a good answer for initial or terminal object in rings?
I have a question about the definition first. Do you require that the unit element is different from the zero element?
Very good question. What do you think that I would do? So the question is...
Probably have to be different.
No, okay. Let's see why. I consider all those things algebraic structures. Not here, whoops, sorry, not fields. So yeah, I want to consider it an algebraic structure, and if I impose this thing, it stops being algebraic. This is not immediate. The fact that there is potential problem is immediate because this law is not an equation, it's a negation of an equation. So it's like already fishy. Maybe you will say somebody will find a different axiomatization, it will be equivalent and such and such. This will not happen in this case. And so let's say this is a good reason to permit this, how is it called? Trivial ring maybe? Yes, yeah, to include the trivial ring, to accept the trivial ring as a ring. And another good reason, maybe you don't really buy this thing that I'm selling with the algebra-like equations only, is like you see the category of these things and you see, okay, that these things that actually have all equations, the categories of these things have very nice properties and they have very nice guarantees. And like if you take this away from the rings, suddenly the world of rings loses some nice properties. What was your... You had your...
I just wanted to say that if 0 equals 1, we just have the trivial ring. That's what I would do.
What about the trivial ring? Sorry, say it again.
If 0 equals 1, you get the trivial ring. That's what I wanted to say.
But is this like an answer to one of these questions, or is it a random comment?
I mean, if you just have the element 0, you can embed it and you can map everything onto it, so I guess so. Yes.
Any of these two ways is unique? So it looks like there's a good candidate for this thing to be a terminal object. How do you have a good notation for the 0 ring, or if I write it like that, is it okay? We understand what I mean, right? Okay. So what is the... Okay, so let's see. Is it in fact that from any ring you can have an homomorphism by mapping everyone to this thing? You cannot break any laws, right? If you had this law, okay, you wouldn't even have this ring, but anyway. So initial objects in rings, yes?
I don't think you do have any, because if you had a ring where you could find like a homomorphism from that ring to anything else,
It can be challenging. If I challenge you to give me a counter example, I think you will have a hard time. Like what? Like.
I had it, I lost it. I don't think there exists anything.
Okay. Anybody else has an intuition on this? So you have a ring. Imagine you have a ring you know nothing about, right? And you want to see if you can map it to somewhere.
If you just map 0 to 0, does that break anything?
You can't do that with a trivial ring.
What?
You can't do that with a trivial ring.
So the trivial ring is out, right? It's definitely not an initial object. That's a good start. We only have an infinite number of rings to check now. We've ruled out the. Okay, so yeah, you have an idea?
Is it like everything else?
Everything else, okay. If it were everything else, but just a second, just to emphasize this, we have already proven that the initial and terminal objects are unique. So in case everything else was initial, all other rings would be isomorphic to each other, which is not the case. You have another guess? Yes, okay? Yeah?
It's the ring 0 and 1 where they're different.
With only these two elements,
I would definitely hope. Yeah, I would hope so.
you will break something. Okay, so I just maybe wanted to give some like curiosity for you to figure some things out. I'll stop this now. Maybe I'll give a spoiler or not. Okay, it's the first one. I'll give a spoiler. It's the ring of integers, and obviously all other is isomorphic things to this ring. And so the new homework is about this one. Why? But please go back to this and try some random things, depending on which of these notions you like the most, or which of these categories you like the most. And as I said, like, to really understand this concept better and not be influenced like thinking, mono is just the category's way of saying injective. Like it isn't, it will happen to be synonymous to some of these things, but in order to understand very well this idea, just investigate it in a bunch of different categories. Okay, great emphasis on the importance of this homework, and if you take a topology course on the equivalent homework of topology. So, any questions? Okay, good. Now, let's see where we were. The idea was to define, the idea actually was to say that I don't get to say that I know what a category theory is about unless I tell you how I get from a category to category. And finally, let's try to see. So what are the arrows between categories if I would like to say have a category of categories? So the idea is that we have an arrow like, we have a category C, and we have a category D. And I want to see what would be a way to go from C to D. And I want suggestions, preferably someone who has not seen it and does not know the answer. Like, let's try to treat this like other algebraic stuff we have seen, where let's say, what are the arrows between groups? It's functions that map things from the category, from one group to another group, such that they respect the things that are important for the concept of group. So the idea will be similar. So let's try to get there together. I want some suggestions. Okay, so what is the first difficulty here, or not so difficult I think, but in a category I have objects and I have arrows, so I have two kinds of things. So I need, if I say that I will translate C into D, I should take care of the objects and take care of the arrows as well. So let's call this F. Since I know that there's objects here and there are arrows here, it's quite probable that this F should map objects to objects and arrows to arrows. So it has like a double character as well. I could even say that it has like I have two things and not one, but usually we just call it F. I could say, okay, I have an F that maps objects of C to objects of D, and I have my F as another part which maps arrows of C1 to arrows of D. So, is that okay? Is that acceptable? So the idea is that I have a category. I will do this weird thing where I try to draw arbitrary categories that look like the letters that I'm using. So like this is C. This is just a convenience for me. So I want something that maps this to this. This will be F. And we will call these things functors. And we are trying to understand what the definition should be. So if I have here an object A and an object B, I should have an object FA here and an object FB here. Does that make sense? Okay, but between A and B, I may have like arrows, like an F and maybe another one, G. And maybe I have an, I don't know, I that goes to C, I don't know. So the idea is that this whole diagram that I have here should get translated into a similar kind of thing of diagram. So I will have definitely an F of C here, but it may change like the shape, or it may change a bit. So I want to see what things are required to maintain. So I have three arrows, and maybe D has some new objects of itself that have nothing to do. They are not mapped by anyone. It's like this functor is not surjective. Okay, and maybe I have an arrow here. Good, okay. So, any ideas? What should I impose? What laws should I impose on my functor, on the functor concept? We have an idea, yes, Vanolis?
The source and the target of the F of an arrow should be the F of the source.
Very well. It's like it should be compatible so that, for example, you will not send F here, right? So since F connected A from B here, consider the big F to be like a translation of C inside D. So definitely, whatever arrow you will little f will become, it should go from the translation of A to the translation of B, so this is out. So this should be like that. Okay. And I could actually encode this saying that f of 1 will get me from arrows A to B to arrows where? Yes? Exactly, thank you. F of A to F of B. Okay, what else? So far, I haven't even touched on the laws of category, right? Because what are I have two laws for categories. We managed to put the things about source and target because you used rich types to describe these things. So actually, we only have two laws: the law of identity and the law of like two unital laws, and the associativity. So the thing about compositions. So the things to be respected are these operations. Give me the identity, give me the composition. So functor should respect these things, right? So how would I write this down? What does it mean to respect the identities? Yes?
The F of the identity of A should be the identity of F.
Perfect. So out of all those things, what we have established so far means that if you have a bunch of and the arrows here, right? Arrows from A to A. So far, you could map anyone to any of the arrows here. Okay, but now we need to respect the identities, which means that the identity, you don't have a say on where to map it. It has to be mapped on the identity of f of a. So let's write it down. So the identity or maybe I will write it like that. The f of the identity of a has to be equal to the identity of f of a. Make sense for everyone? Okay. And the other thing, let's speed up a bit. Yes?
The f of the composition should be the composition of the respective types.
Exactly. So, like, if you compose this with this here, you will get an arrow from here to here. If you translate this arrow, you already know that it will be an arrow from, I don't have f of c here, okay. It will be an arrow from here to here, but which arrow? It has to be the composition of this and that, because D can give you an answer on what it means to first do this arrow and then do that. So, okay, let's write that down. The f of fog should be the f of f of g. Does not make sense. Okay, so it doesn't matter. This is like a commutativity of a certain diagram. It doesn't matter where the translation happened. You could first compose and then translate, or you could translate these two and then compose, you will get the same arrow. So it's exactly the same idea pretty much that happens. This is why I think that, there cannot be much arguing of what's the correct notion here for a functor. Does that make sense for everyone? Yes, okay. So let's see an example. We could start, usually I do that, but I don't want to do this now. We could start from like silly examples, okay, let's do it now. Let's take the category 2, right? Okay, the category 2 looks like that. And let's take the category, I don't know, 1, okay? So the category looks like that. Do I have a functor from 2 to 1? Yes? Okay, which one? You have to tell me, where will you map this? Sorry, I should use a star and a bullet, not a bullet and a bullet. Okay. So, where do you map the bullet? Exactly, you don't have an option here. Bullet, where do you map this arrow and this and that? There are 3 arrows here. You don't have an option. All of them will have to get mapped there. And the question is, does this satisfy the laws? And the answer should be pretty much obvious yes, because there's only one thing. The only way to break laws is to have to end up with 2 things that should be equal, and they are not. But here you only have one thing. You mapped everyone to the same thing. For the same reason, that's quite trivial that if you map every element of a group to the identity, you cannot break any equations. Okay. So not so interesting, obviously. Let's see something a bit more interesting. So consider you have. Let's go back to types. Let's go back to the category of types. And you can think of types of a programming language if you like, but probably this will end up breaking some kind of law of category. And even though some community, like the Haskell one, actually tries to advertise that we have a category here, it's like if you forget some things, this becomes a category. It's easy to forget those things. It's not very honest. But for our purposes, we can think of the types we know, and we will not cheat, and it will not be, we will not deceive anyone. So, like, we have these types, like alpha, beta, blah, 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 and we also have seen what these types are. Anybody remembers? I mean, it's been a while that I haven't used it. What is a set of alpha? What's the type of this thing? Everybody forgot this. Vacations have this effect. Holidays and all that stuff. Yes? Yes, I mean, first question, what is the type here? Yes? No, wait, you answer the more difficult question. You answer this question, what is the, let's say, the type of this? Type to type, you could think of it like that. So this thing is a type, And we haven't mentioned and discussed like a hierarchy of types, but let's forget that it's a type, okay? So, which type is it? How do we describe its elements? Yes? Yes, it's the element, it's the type of all sets whose elements are of type alpha. Okay, so I have this thing set that, as Lazarus said, I consider this, it takes a type and gives me a type, right? So I can apply set to objects, to types, and I get back types. And the question is, maybe, if I realize that I can apply it also to arrows, which means functions between types, then I can check to see if this thing, set, is a functor, right? In this case, it will not be a functor from one category to a different category, because it just happens to be like from this category to this category. To scare people away from our stuff, we call these things endo functors. But I mean, if you remember endo, or if you're Greek, it's not really scary. Like it just means functor from something to itself. Okay, so it is a functor. Okay, from the category of types to the category of types, I can apply it to any object, and it will give me back an object. So I apply it, for example, to this object, which is lying around in my world of types, and it will give me back this type. Example of elements here is 3 and 5. Example of elements here is like 5, 7, 8. The empty set, the whole of n, blah, blah. Okay, so I applied set to this type, and I got back a new type. Can I apply set to arrows, and what do you think this should be? So like, think of your favorite function, let's say from, I don't know, from n to booleans. Maybe it's the function even that checks if a natural number is even. I don't know if I got it right, and this is your favorite function, but let's say you have this one. So you already know that this set thing will end up being, out of this, you want to get something here. From sets of natural numbers to sets of booleans. And like the question is, what is this thing? We'll end up calling this set even. So let's give a concrete example. Like if I give you 7, okay, I will start from a different example, sorry for that. I will start from naturals to naturals, and I will consider the function double. Like, okay, so if I take this thing and I apply to it the shifted, as we say, or the elevated version of this double. It's not really double. If I say double, I have a type error, right? But if I type it, if I apply it here, what would you think I should get? Yes? Maybe. Yes. 6, 8, 16. I mean, it looks like the obvious thing to do. So for my next example, like if I have like this, and I map here like the elevated versions of even, what should I get? Yes? The singleton false. You are thinking of either bugs or lists, I don't know. So it's just false, right? It's a set, okay. But as soon as an even number sneaks here, I will get back the whole of the booleans, right? Okay. So we are meeting again a concept we already know since we have studied like a set theory. What do we call this thing? Somebody? Yes? The image. Sometimes we even change the notation. I don't know if you've seen this, like set theorists might use like something like that to say, I consider the image of this thing, and they say, aha, this is what? This is all the f of a's such that the a comes from big A, and we call this the image of A under F. And the question is this a functor? Okay, so if this is let's call it like it's a power set. Okay, so okay, so if I start using set theoretic language, this set here, I mean it slipped my tongue, but how would the set theorist write this set? The set theorist doesn't have a type, has a set, and now wants to go to the set that has sets whose elements are of this set. So this would be, it's the power set. So like you have the power set, you can apply it. You have an A. I will draw the image here. I think it's make things a bit clearer. And then you apply the power set to A, but the idea is you can also apply it to F. And this is just a different notation, a less specific one. And therefore you get to say that you have a functor if the laws apply here. And what the laws would be, I need to respect the identity and the compositions, right? So it means like that, let's try to figure this out. If I have the identity here, from A to A, here I have the power set of A and the power set of A, and here I will have like the power setized identity, if you want to call it like that. And what do I have to respect? It will go to indeed to the identity. Does it? I mean, if I try to make this thing, it will be all the E day such that A comes from A, from let's say X, right? I don't know. I'm a bit lost here. What was I trying to show here? Somebody help me, please. I got lost.
Small a. Your identity, subscript big A of small a.
Identity subscript big A of a small a. Yes. Okay. Thank you. Yes, okay, and this is, thank you, so this is all the little a's, which is just A, which means that this is equal to the identity I had on A. Does that make sense? And this identity should be subscripted by power set of A. Okay, thank you, Manolis. So, like, I just verified the identity. Similarly, I leave it for you to verify the composition. Now, together with the image of something, you probably learned in set theory the pre-image of that thing, and definitely this will not be it doesn't even have chances to be a functor because it's also applied. I mean, you can apply to A and B, and you get the power set of A and the power set of B, but the pre-image goes the other way around. Okay, but it still respects things in a kind of weird way. It like flips everything, but other than that, it's okay. So when this happens, we say that this functor is a contravariant functor. So I will type these up later on. You know, I polish these things later, but it's like, okay, covariant is always implicit here, and it means what we just called functor. And contravariant means it's like a functor, but it flips everything. And okay, so I will just tell you to check that the pre-image, maybe you have seen it like that, is a contravariant functor, and the image we have checked half of what we need to check is a covariant functor. Okay, sometimes we say functor and we just mean it's obvious. You will figure out if it's a covariant functor or a contravariant functor. Questions? Okay, so an image I want to have, like when I have before I give you an image, in programming, you do have, I know I have some people who have seen this, so I need to mention it. You have a similar thing to set. You have seen probably lists where you get, this is also, you can also see this from type to type. So you can try to say, okay, maybe this is a functor, and in order to tell you if it's a functor or not, I need to tell you also how it acts on arrows, which means functions. So someone who has seen lists in functional programming or something might help me here. and tell me if I have an arrow from A to B, to beta, from alpha to beta, and I want to go from list of alpha to list of beta. Actually, if I consult someone who has never seen this with a similar example, like what was my example here, if I have a list here, which is this, 2, 7, 11, and I don't know what, and 10, and maybe 2 again, just to emphasize that it's a list. And if I try to apply like the even function, I should get back a list of booleans, right? So I get from a list of natural numbers to a list of booleans, and the question is, what is the obvious list of booleans that I will end up here? Yes, Saradi? You are using numbers, 1 and 0. They are booleans, so you have true, false, false, true. Okay? Yes, and let's say I suppose it's true, false, false, and true again. Okay, so I got from a list of numbers and list of booleans. Arati, have you ever seen functional programming with lists and stuff like that? Yes, okay, thank you. So it's a kind of very natural thing that this is the function. I mean, even if you see it like that, apply this function to that, maybe you will say it's a type error because even goes from natural numbers to booleans, and I have a list of natural numbers, but the idea is do the obvious thing and shift this little function that operates between natural numbers to booleans so that it can operate from lists of natural numbers to lists of booleans in the obvious way, okay? And yeah, so already figured out what the obvious way is. Somebody can tell me how we call this usually in programming? Yes? Yes, it's map, also known as fmap maybe, and this f comes from functor because the fmap is the idea that every functor should have like this thing. It's quite a common name. Usually you meet it first time in lists and you call it map. So technically this is, the proper name for this is, it should not be fmap or map, should be, it's the listified version of L. It has been elevated to list, right? So when you want to say that list is a functor, you have to say how it acts on objects, and you say, okay, it takes a type and gives them back the type of lists of elements of this type, and how it acts on functions. You then give me a function and maps this function to every element of this list and gives them back the list of the outputs, okay? And once you do that, you can check that it's indeed a functor. Like when you're programming in a language that has cool stuff like that, now it depends on how many cool stuff your language has, but like for example in Haskell, you have these things, but on the other hand, you don't have how to actually, inside Haskell, say that it is indeed a functor. So you will probably see a comment if you see like the code of someone who implemented the thing and says it's a functor. They will say how it acts on objects and how it acts on arrows, and then it's like, and I promise that I have checked that it satisfies the functor laws. It's like, okay, I believe you maybe, but it's not something you can verify within Haskell. What are these laws? I mean, the community knows them, the programmers know them, the compiler knows them, but it's like, we believe you when you say you proved it, and you don't get to like, maybe the system will permit you to define a functor that's not a functor, but definitely the community, if it pays attention, they will complain that you're breaking the laws here and you shouldn't do that. So what are the laws here? Like in, let's use Haskell notation maybe. The map of the identity is, yes? No. So like imagine you have this this list here, and you applied the identity. It means that this got to 2, this got to 7, and this got to 8, but your friend, and this became a list. But your friend, instead of doing these little identities here, just called the identity directly to this. And the idea is that these two approaches are the same, commute. So how would I write that? Yes? Yeah, it's the identity. People will only write it like that, but there's polymorphisms here, and you get away because of that. So this would be like the id here, and this would be like the list of alpha, right? So these are, you are calling the identity of natural numbers here, while here you're calling the identity of the list of the lists of natural numbers. Okay. And what's the other law? Map. Yes.
Not the synthesis, not the...
Exactly. Which means that if, I don't know, I could go on with a different function here, maybe a double now, I don't know, 14 and 16, I will get this to a list. And now you start to think that actually if you teach your compiler those kinds of equations, you get a much more efficient program, because let's say, obviously you will imagine that you have a list of 1 million elements here. So if you don't know this equation, you might say, okay, first I need to do 1 million steps and double these things, and then another 1 million steps and I don't know, multiply them by 5, I don't know what are your functions. And then you will have to traverse this list like 2 times. While if you know this thing, you say, no, actually I will do it like that. And the result will not change. And if your compiler knows this kind of equations, you may do the stupid thing, and the compiler substitutes for the clever thing. Because if you have mathematical equality, you can substitute one for another. So, any questions? Yes?
Πιο πάνω στο παράδειγμα με τα set.
Okay.
Πέρα που είπαμε
Για
για το...
το reverse image, no.
Για το even. Είπαμε αν υπήρχε και ένα 2, θα ήταν τότε θα έκανε map στο false, true, όχι στο true. Σωστά.
Yes, so if there was a 2, technically you can think that they map to true, false, 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 but this is a set, so this is the set of booleans, right? Okay. Any other question? So, yes.
Το compose,
Uh-huh.
είναι ας πούμε σαν να έχω στην αρχή μία σύνθεση και μετά είναι σύνθεση συνθέσεων.
No, it's not a composition of compositions. It's like, I think this is a good picture here. If you are like in the natural numbers and you consider this diagram, let's say here, right? Okay, I should write it down. Let's say from natural numbers to natural numbers and then to, okay, booleans. I like this. So the first one is like double, and the next one is like even. Okay? So you can compose them in this world, and you get a function from natural numbers to booleans, right? And the example would be like 3, 2, 3. Let's keep it simple. And then you will go to 4, 6. And then you will go to, okay, I realize it's a kind of silly example because everything will become even, but okay, let's ignore that. Is that okay so far? Okay, so you have this function. Which function I'm talking about? The one that maps 2 to 4. This is even. And you are applying it like that. Sorry, yes, you're right. Thank you. So this is double, double. This is the even and the even. And the idea is that you should have functions that go shifted functions, elevated functions that don't go from natural numbers to natural numbers, but actually go from lists of those things to lists of those things. So you have the big versions of double and the big versions of even. So let's call that, I will use a proper name, the LD, and this is the L even. So like this law that you said, like it's a composition of compositions, it's not really a composition of compositions. It's like in this case, I'm composing this with this to get this little thing to this little thing, and then get this little thing to this little thing, and then I'm making this into a list. While the other composition is composing these two things. And the idea is that this equality means that whether you do it like that or like that, these commute. It's the same thing. Does that make sense? Kapos? I don't like this. Okay, so let's take a break, like a 9-minute break. Sorry for that. And let's come back at 12:15. Okay, so there was a bit of a mess that Manolis discovered, and I already corrected. I will update the PDF, but I don't want to focus on this now. Let's see. Okay, so like in general, the thing I want to keep in mind here about functors is like this idea that you have one category and possibly a different category. And as soon as you manage to get a picture, let's say, of this category inside the other category, in a good way that respects things, you get to say that you have a functor. So like, maybe if I have a functor, let's paint this functor blue for some reason. And let's call it F. It's like I have a blue copy of the category C inside here. And in this category, I have stuff, objects, and arrows. Let's say I have like something. I'm just like drawing a specific arrow here. I have a bunch of arrows, a bunch of objects. Maybe between A and B, I have a bunch of arrows. So correspondingly, I will get something like that. This will be F of A, F of B, and this thing will also get translated to be an F of little f. Does that make sense? So now I can consider that I have a blue copy of C inside D. As we've seen, another functor would be maybe more brutal and send everything here to this thing. So it's like you got C and you condensed it to something very small, and this is also a picture of C, and which is valid in this case. You will not break any laws. But the idea is that in some sense, the diagrams that you have in C, they translate to D, and whatever commutativities you have in this diagram, they are still respected. Maybe they become completely trivial because maybe some square became just a point, but like the laws that you have, the functor laws, help you in the sense that the diagrams you get commute. So you have like this image, this blue image of C inside D, and I want to start with this topic even though it would be like, I was planning to do it a bit later, because I definitely want to be done with it. So now comes a tricky question, like you have this blue image of C inside D, applying the functor to C. Question just to see if everybody is with me, can I apply the same functor again? So I get the F of F to the blue thing, let's say. Okay, I see some annoyed faces, and this is the faces you should have now, because I have a type error, right? Because F gets me from C to D. It's not like the previous example, which was an end of functor, like I could apply the list twice to get the list of the list, to get list of integers, because my functor there was from one category to the same category. But now I'm going from a category C to a category D, so I cannot keep applying F here, right? Hope this makes sense. On the other hand, like I could apply a functor here, G, and go to a different category E, and I could compose these functors, and the idea is that we're reaching the idea that we indeed have a category of categories. Some things need to take care of, but I don't want to worry about this right now, where the objects are categories, the arrows are functors, and everything like all the laws are respected. Okay, but I want to see something different now, and say, okay, you got your favorite way of mapping C inside D, and you got a blue copy of C, but I have my way of mapping C into D, and I will call this G. So in this sense, it can very much happen, it's quite often that this thing happens, where you have like a blue copy of C and a orange copy, this is orange, copy C, and they go something like that. I will keep doing this convention that I told you, that I like to draw things that look like this thing. So like I have this blue C there, but I also have an orange C there. So this thing is like it's like F of C, and this will be like G of C. Does that make sense? So I have a blue copy of C, everything got translated, and here maybe I have something like, this is G of A, and this is G of B. And obviously, now if this was a contravariant functor, G, it would still go from C to D. Don't think that contravariant means that it will go from D to C. It's still from from C to D, but if it were contravariant, it would be, the direction of this arrow would be like that. It's not, so for my example, I'm taking two covariant functors, so it's like that. And I have like G, big G of little f here. So you have your blue copy and I have my orange copy. What is an obvious question to ask? I hope it's an obvious question to ask, otherwise I will pretend it was obvious. Yes, Arati? For the what? Is that? The intersection that I drew there. Okay, I drew an overlap there because they might have this intersection, they might not. They could be like that. For example, maybe they even agree on some point and they don't. I want to keep it completely like not impose anything. Maybe G mapped the whole of C inside this little point and all the arrows in C to the identity. As we've seen, this is a functor, so this could also happen. Imagine that a C is very small and it looks like that. So, any other suggestions of like next thing to ask? Yes? Whether the functors are equal. Okay, it makes sense to, like what would equality of functor means? We could influence ourselves from the equality of functions and say, okay, they're equal if they map the same things to the same things, right? I want to like look at this in a more geometric way, maybe. You have a shape there, yes? The size of the, okay. The size has is only related to one of these things. You can ask what's the size of, okay, you mean like how they compare to size, the blue and the orange? I like this more. Okay, you are in the right direction, I think, yes?
Αν τα FC και G είναι ισομορφικά.
If you could ask if these happen to be isomorphic, even though we don't have this thing, but you can imagine what should be two categories to be isomorphic. Okay, so where I'm hinting to go at here is like once you have two interesting things, let's say that blue and orange are interesting, it makes sense to ask how I get from one to the other. So if you got the blue thing, you embedded C inside D, you got C inside D and became blue, and I did it in an orange way, is there a way that your blue thing can become my orange thing? Does this question make sense, even if it wasn't so obvious? So my question is there a way to transform this blue thing into an orange thing? Yes? Wait. Do you want to give a suggestion of how to do that? Okay, before we get to that, so I'm looking at something like that. What would it mean if you have a functor and I have my functor? Is there a way to get from your functor to my functor? Okay, and okay, so I think you have the microphone. Yes.
Φανταζόμαι σαν μεταφορά, δηλαδή πόσα σημεία χρειάζονται να μεταφέρουμε ή να στρίψουμε για να πάρουμε το άλλο.
Pretty much the question is like, what do you have to tell me in order for me to say, yep, you convinced me that this is a way to get from the blue to the orange. Does that make sense? Yes. Okay, so probably like you should be able to map f of a to something. To where would you map this? Obviously, I think. To G of A. Okay, but how will you map this? So like you need an arrow like that. Okay, what else do you need? Let's draw the things and then see what we need. My point here is I will bring this here. I want to somehow transform the blue thing to an orange thing. Like, So I will definitely need, I will definitely need to map f of a to g. F of a will move, let's say, and go to g of a. What else should happen? Help me here. Yes?
That's the big, so big,
So these things should happen, at least these two things. And where am I now? Like, and you say that these things should happen as well in some way, right? Does that make sense? Okay. But these three yellow arrows that I have drawn here, like, where do they live? They are arrows in which world? Because all these things happen inside the category D. So I will say that I define the way to go from the blue to the orange if I have a way. So this is an arrow in C, and this is an arrow in C. This is not exactly an arrow in C. Can anybody guess what I will substitute with this arrow with something else in C? Any guesses? We have seen this like once or twice. This is similar to an answer that Panos gave in about product, and he said something like, yeah, you map the object to the object, you need to map the arrows as well. We didn't manage to make this idea formal. We can make it formal, but what did we do then? It's the same thing here. Yes?
We map pairs of objects connected with an arrow.
So this is what we have here. Like we have this pair of objects here, and we have this pair of arrows, and they were mapped there. But you need to be careful with the same thing that you always need to be careful when you define anything in this last lectures. There is a square here, right? Yes?
We just require that it commutes, right?
Yeah, the square has to commute. So whether it commutes or not, who will give us the answer to this question? Like I picked this arrow, and I picked this arrow. Do I get to pick the fact that it commutes? No, this is something that is either happens or doesn't happen. And who gets to tell me this? I mean, not who. What? Sorry?
The maps FA to GA and FB.
So, exactly, all those things live in D, so I can ask D, hey, does the square commute? Okay? And all these squares that will show up have to commute, right? So if I have this, I get to say that I have a way to transform the functor f to the functor g, and now let's try to give a more like explicit definition of what's going on. How many arrows do I have to say to give to you? I mean, in my image, it's 2, because I'm only showing 2 objects. But look, it was not 4, the things, or 3. It was not 1, 2, 3 things that I need to show you. I need to provide 2 things. 1 for each of what? Yes?
Object.
Of which category?
D.
Yes, again?
To image this is D.
So, if you index all those yellow arrows, what are your indices? I think you're seeing it in the right way. You're saying it in the not so right way. Like here, let's give them a name. Let's say that I want to call this thing alpha, and I want to give subscripts here. So I want a subscript to this alpha and to this alpha, because in general I will have a family of yellow things. Let's all collectively call them alpha, but like I want indices to refer to this one and this one. What would the index you would choose for this one? Question is for everyone. Well, what if you have an object here that has nothing to do with these things? Will you want to map it somewhere as well that doesn't? No, it's not that. Sorry, this. Okay, I'm using Greek letter. Maybe this confused you. No, it's like I don't know, a fancy letter. Usually sometimes fancy letters are Greek. I know we are Greek and they are not so fancy for us, but it's like this alpha here is not a type, okay? It's like, I don't know what would be fancy here. It's very common to call it alpha, so I'll call it alpha, okay? Or beta, or stuff like that. It has nothing to do, let's say that for this discussion, we denote types with these things. A, B, uppercase. So this is my alpha here, okay? And the idea is, in order to give you an alpha, I have to give you all this bunch of yellow things. Okay, let's say, how many yellow things do I have to provide, yellow arrows? As many as what? I don't want to say 2, okay? I want as many as what, yes?
C0.
As many as objects I have in C, right? Because what happens here is that if you focus on an object of B, okay, let's see. If you focus on this, will become messy, okay? So bear with me. If you focus, okay, let's focus on A. You're on A, okay? And you can map it, you can ask for the blue A and get here. Or you can ask for the orange A and get here, right? Does that make sense? Okay, and you can do the same for B. For B, you can ask for the blue B here, and you can ask for the orange. It will become messy. Sorry for that. I don't like this, but okay. Does that make sense? Okay, and you have to tell me so there are 2 different translations for each object of C. And you have to tell me, for each object of C, how to go from the blue translation to the orange translation. So how many yellow things you need to give me? As many as objects you have in C. So a natural index here would be like, this is the alpha that deals with the object A. And this is the part of alpha that deals with the object B. So in general, for each object in C, you will have to tell me how to go from the blue image of this object to the orange image of this object, right? So yeah, tell me.
So, okay, I think it might be useful to emphasize this because I kind of had an objection initially, and now I see why the objection was not valid. Initially, I was thinking that the blue functor could merge some objects of C, and the orange could merge some other objects. So I wasn't seeing how to go from one merged object being the blue.
Okay.
2 different things in the orange. So we can actually have 2 arrows leading from the same object in the blue to different objects.
Yes, exactly. Okay, yeah, this can very much happen. So if I want to write down the law that this needs to satisfy, it's like every time you have an arrow here, you can create a blue copy of that and an orange copy of that, consulting the functors that you have, the blue functor and the orange functor. And now the idea is that the natural, I haven't used the name so far. So these are called natural transformations. And luckily, they have a not so scary name, like in the functors. They are very natural. Natural transformations. Okay, so I can ask for my natural transformation how to go from the blue A to the orange A, and I can ask how to go from the blue B to the orange B. And obviously the condition is that for any arrow that I pick inside this category, what happens? Like, somebody help me here. What do you think I have to do? I mean, Konstantin's already mentioned this. And it's like every time that I ask something that is a square or a triangle there, it's the same answer. This has to commute. Okay, so in case this happens, you get to say that this alpha, which remember, one alpha is actually a bunch of things, all this collection of yellow things that you told me, this way to translate blue translations of objects, blue objects, let's call them blue objects in D to orange objects in D. For each one, you told me how to go there. All these squares that show up need to commute. Is that acceptable? About like further constructions, we will not use anything. Then the basic terminology of categories pretty much ends here. There is one thing that I will need, there is one thing that's still missing, and this is something that was missing already in the world of, in the logic and also in the world of orders, because we have seen products and then we have seen sums, and we have seen 0 and 1. And maybe it's kind of already weird that we have seen first multiplication and then addition. We have talked about that. But there is something missing still. And what's that thing that's missing? Like, after you learn addition and multiplication, what's next? Exponentiation. And on the other hand, we have something, we have talked a bit about that. We have something on the logic side, which we haven't found so far an equivalent in the order theoretic aspect or the category theoretic aspect, and this is implication. So just to not bore you or like tire you very much with new categorical stuff, let's remember a bit that we have forgotten about implication, and let's remember what kind of rules we had for the implication, which was like this. You have I hope we remember what this means, right? It's like knowing that A is true, I can prove that B is true. And from this, if I have something like that, I should be able to do this. Like A implies B should be true. This would be like the introduction of implication. And how do I use implication? So if I have that A implies B is true, how do I use it? It's useless unless I also have A. So usually you see it as something that I guess some of you already know the name. It's a Latin name. Okay, so let's write down. Yes, it's like you have this and you have that A is true. From this, you can infer B is true. And this is usually called modus ponens. It may seem a bit arbitrary. I mean, if you do the connection with programming and with types and that we have, you say, okay, wait a minute, this is the arrow, right? Because I know that if I have something of this type and if I have something of that, this is how I use functions, and this will allow me to create something of this type. And now your only worry is, how will I denote that? And we denote it like that, okay, for some reason. I could denote it in another way, but this is how we denote it. But maybe it's like not so clear how one would reach this. So I want to see this as kind of an inverse thing to that. The idea is that you want this A implies B to somehow encode the information that there was a proof from A to B. So remember, every time we were looking at one like introduction rule, we asked, okay, I don't know, like for conjunction, we said, okay, information went in, right? I have A true and B true, and information went in when I created the conjunction. So when I will want to use the conjunction, I should be able to extract this information. Do you remember this? I mean, this is the idea that like guides you in order to figure out what the logic will put. But if you see it like that for implication, what is the information that got in from here to there? It's like that I have a proof from A to B, right? So if you give me that, I should say, okay, then out of this, I should be able to get the fact that from A I can prove B. I will give you like a minute to think and tell me what's the connection between this and that. This is what you probably have seen in logic or whatever. This is probably what you would come up with if you were following closely like what we did within disjunction and conjunction and now implication. Probably the elimination you would come up with would be this one, not this one. This kind of looks weird. So are they kicking us out? No, they don't have the right to kick us out for the next 20 minutes. Okay, so let's look at this. This is like what you would probably figure out yourself. This is what your logic teacher told you. So what's the connection between this and this? I want somebody to see it, but I want to give like 1 minute for everyone to think. Okay, let's think of that. Look at this and look at that. Like the correct answer is like just a single word. Let's see. Okay. You can describe the correct answer using one or more than one word as well, but okay. Does anybody have an answer that's like one word only? Okay, no. Areti, what was your answer?
Το δεύτερο μπορεί να σημαίνει δύο πράγματα και το πρώτο είναι σαν εφαρμογή του δεύτερου.
This could mean two things. What are the two things that this could mean?
Βασικά, όχι ακριβώς αυτό, αλλά ότι στο δεύτερο δεν ξέρουμε αν το είναι του. Οπότε το δεύτερο είναι ο κανόνας και το πρώτο είναι.
Here, okay, I'm not sure how to understand this, that we are not sure if something is valid or not. Here it says the following. If these things are valid, right? I'm not saying that either of them is. If these are valid, you can infer this. And here you're saying, so if these two things are valid, you can infer this. I'm giving like a hint with my voice as well as to the word I'm looking for. While here is like, if this is valid, then you can infer this, that as Areti is saying, what is this saying? That if this is valid, then you can infer this. What's the one word answer? Yes?
Carrying?
Yes, okay. So this is the uncarried version of this. This is the carried version of this. This is the carried version of this. It's like we have pushed this to become like after the arrow, right? So if you visualize this as some kind of linear form of this saying, if you have this, then if you have this, you can prove this, right? So instead of saying this, I could say, if you have this and this, then you can prove this, okay? And now, continuing with all these things we have so far, I want to reach the order theoretic interpretation of what's going on here. Because remember, we were trying to see what order theoretic properties. Oh, sorry, yes.
Is carrying just a deduction theorem?
It looks like that. Because the deduction theorem you have in mind says something like, if you have something like that, is this what you're talking about? You can pass this A on the other hand side.
Yes, you can take it and say, no hypothesis imply that gamma implies A, B.
This will be the more general thing. This is you can see this as some kind of carrying as well. It kind of means that implication, what we're trying to figure out here or to establish is that this weird logical symbol internalizes this external symbol. And it internalizes it properly. Like if there is a proof, if you can find a proof here, it means you can find an inhabitant of this type. And if you have something of this thing, it means that indeed there is a proof. It's like a soundness and completeness of these two things. It's a good internalization of the external concept. So if we remember like the order theoretic properties we have so far investigated on this relation, okay, rapidly, do I have a terminal? Remember, I'm writing A less than B to mean this, that from A true, I can prove B true. Okay, so I have a proset here, okay? Do I have a terminal, initial and terminal elements, and what are they? Yes?
For initial boom.
Yes, you mean yes, this Folsom, yes, boom, yes. And for terminal? Do I have a terminal object? What would a terminal object be? Something that I'm looking for something that if you give me anything here, I'm guaranteed to be able to prove this thing. What is something that is always provable out of whatever you give me? Yes? Yes, the boom, maybe the opposite of boom, I don't know. The top, or the truth, the always truth. It's a proposition that is trivially always true, right? So we do have initial and, I'm confusing now categorical terminology, which I want to do next. But right now I'm in orders. So I do have a bottom and a top, which are, I denote them by bottom and top as well, which are like the always false and the always true. What about products and coproducts? We've met them as well. What does it mean to be a product? Sorry, I'm using categorical things again. I wanted to say joints and meets. Okay, so do I have meets? What does it mean to have a meet? It means that this will be the meet. It's a lower bound. So I should have this. And also it's the best lower bound, which means that any other thing that has these two things I guarantee that mine is better, which means that in this, okay. Is there such a construction in the world of logic and propositions that I'm studying that satisfies this? What are meets? I mean, even if you don't know that, you look at the symbol we're using for meets and can deduce what it is. What is it? It's the conjunction, right? So A and B implies A, and A and B implies B, and you say, aha, these were like the first things I learned in order theory about meets, but you realize that these are actually the elimination. These are these, right? From this I can get this, and from this I can get that, right? And the other thing is what? It tells you that if you can prove, if from C you can prove A, and from C you can prove B, then from C you can prove A and B. This would be like the introduction. Okay, so we do have meets, and what's next? Joins. Do we have joins? What are the joins? Is the disjunction, and instead of having two elimination rules and one introduction rule, we have two introduction rules and one elimination rule. And so here is this idea. We are studying logic. We have true, false, conjunction, disjunction. We found this connection with order theory, but in logic we also have implication. So it makes sense to us, what is the equivalent thing of implication for orders, right? How can I describe order theoretically an implication? So let's do that now, and next we'll have to do that in the language of categories as well, which is like more general because you see more than one arrows from objects. It's not so thin as in prosets. So I'm looking to describe order theoretically the properties of implication. So let's see, what's so special about implication? I will denote it like that. So the special thing is that if I combine it with B, okay, maybe I should change the letters here, I don't know. Maybe you prefer like that. Okay, let's write it like that. What's so special about this thing? If I combine it with A, I prove what? B, thank you. And how will this combination mean? How will I write it? If I'm in logic, I will say I can write it like that, a conjunction. Now that I'm saying this order theoretically, it means that from this, if I meet it with A, I can prove B. So it has to have this property. Whatever this exponentiation is, this implication is, let's call it, for the time being, I, to remember this implication. So I has to have this property. It has to be like an operation between, the output of an operation between B and A. We will end up using it like that. But combined with A, it has to be able to give me B. Am I done? Sorry, thank you. Am I done? I mean, even if you are regular, I don't know, to go home and whatever, but you should know that I'm not done because I've done half the job. All the other things I have described so far have the following format. It does these things, and then part 2 of all these definitions. And it's the same in order theoretic and categorical definition. Yes? No? Yes? Now you're kind of, okay, it's a good, I want to say that you are cheating, but it's great to cheat because this is the whole concept. You know something in here, let's translate it there, but like, if you forget about this thing, and you are like a student only of order theory, or only of categories, so far all these definitions, the nice definitions you have the following format. First of all, if you give me these two objects, there is something that does this, first of all, and secondly, no. This is the categorical thing. Like it's unique and something else. And this something else is common to the order thing. So if you further go to the categorical thing, you have to say it's unique in a strong sense. It's the best one. So this is what I'm trying to pass here. It does the things it needs to do, and it's the best among all those things that do this. So if I stop here, give me a very bad thing that I could plug here and say, aha, this is the implication of B. Give me something that if I combine it with A, I can definitely prove B. If you think logically, or if you think order theoretically, something that if I meet it with A, it's definitely less than B. Yes, Lazarus? B itself, okay. It's not.
I think it's the most trivial.
Think something way more destructive than what you're thinking. Arati, what was your guess? The bottom. Like if you meet bottom with anything, it's already bottom. It's definitely less than anything. You can absolutely prove anything. So this would be like the worst of the worst. So we know that in this case, best will not mean least. It will mean greatest, right? So this is the next thing that I write is like, how will I write it? The same conventions that I also have. If you have any other candidate, what does it mean that it's a candidate? This is why I always use C. It means that combined with A, it proves B. What do I want to infer? I want to infer that my guy is better than your candidate. Okay, so indeed we will denote this like that. I will denote as sometimes it's called like this. There's a little arrow here to remind you of implication, but at the same time this is a kind of bad notation because maybe you think you're doing logic, but this is like an operation in the same sense that you have this and this. Here's another binary operation, and it's also written like that, and this is called exponentiation. Be careful, it's B to the A and not A to the B. Okay, so we should see what kind of things we can do if we find out that in our poset we have joins, meets, exponentiation, zeros and ones. So if you are in a lattice that has exponentiation, lattices that have exponentiation actually are called hating algebras, which is like the penultimate concept that we will meet in this course, hating algebras. This means lattice plus exponentiation. I don't need to say something about joins and meets because these are already implicit in lattice. And sometimes you will see as a definition that's a distributive lattice that has exponentiation, but actually you can prove this. So here's a nice exercise. Prove. I will give you a hint, but not now. I want you to try this without the hint. And I think you will find a proof that doesn't use the hint. And then I will give you a hint and you'll find the second proof that uses the hint. So, hating algebras are distributive. The only hint I can give you is that you have completely ignored some exercises of lattices. And there the idea was to define and observe that there are lattices that are not distributive. So obviously, you will need to use the fact that in a hating algebra you have an exponentiation, okay? And the good thing is that as soon as you have this thing, you can define negation. Negation, I will denote it like that. I can define it like, anybody has an idea how I will define negation in a hating algebra? Remember, I'm in a hating algebra, which means I have top, bottom, joins, meets, and exponentiation. Now you can cheat the way Konstantinos was cheating and say, how did we define negation in logic? Yes?
Το A είναι μικρότερο από το bottom.
You could, okay, this will be, okay, we'll reach what you said. We will reach what you said. Here what I was thinking was like A will imply the bottom. This will be like the not A, which if I think about what does that mean, it means that A is less than equal to bottom, and it also means that together with A, it proves bottom. I'm just translating what this arrow means, okay? So inside any hating algebra, you can define negation by this thing. And okay, I do have 3 minutes, so I will give you some like teasers or spoilers. Let's say a teaser for what's going to happen next. We will define a different thing called complementation, and I don't know how I should denote it like right now. And we'll define, we'll reach a different concept called Boolean algebra. Both of these things, hating algebras and Boolean algebras, are special kinds of processes. Even more, they are special kinds of lattices. But Boolean algebras are fewer. I mean, any hating algebra, I always confuse when I say this kind of things. Every Boolean algebra is a, so we have like, I will draw it and I will not say it. So I will have hating algebras here and Boolean algebras here, and you will not force me to pronounce this because I will say it wrong. So it's like that, okay? Which means there are hating algebras that are not Boolean algebras, and the idea, I don't want to keep this from you, it's good to have this in mind. The idea is that Boolean algebras are for like classical logic. Remember, classical logic means that we do weird stuff with the law of excluded middle and stuff like that. And the corresponding concept for constructive logic, which is the logic we are using here, will be the hating algebras. So the idea is that if you manage to prove a certain thing inside the hating algebra, it means that the thing you've proven, if you look at it as a logic formula, it's valid constructively. Does that make a bit of sense? We'll see it a bit more in like a whole lecture. Yes? Not necessarily. For example, a good example is like the double negation law. So in any Boolean algebra, it happens that the negation of the negation is the same thing. So we will define a hating algebra in which this does not hold, and then we will say, aha, maybe, not maybe, definitely, this idea of negation here and the idea of complementation, which is how it's called in Boolean algebra, are indeed different concepts, and they coincide in certain cases. So we have like, okay, we don't have 1 minute, I was going to say that, but I would like a suggestion now for 1 or 2 minutes, please allow me this. suggestions of how I could define the complement in an order-theoretic way. So what properties should have? I have an A, and I want to reach the idea of, I don't know, something that's called the complement of A. How should it behave order-theoretically with respect to A? Like, let's be influenced by the classical knot, maybe, or even better, by complementation in sets. Yes? Give me a law that you think it should satisfy. Because it should have the same format. It has to do these things, and it has to be the best among those that do those things. It's always like that, right? I want like one of those things that has to satisfy. Yes, Arati?
Not A.
What is the knot? You mean this thing? No, let's try to forget this knot. What do you mean this thing?
Το συνονοτορικό χωρίς το α.
But they are not sets though. I know I told you to get influence from sets, so I want an order theoretic thing. Lazarus?
They should be comparable.
Not incomparable. What's the thing you mean?
A not to be less than the other A.
This should be the word you want here is inconsistent. Like if I have both of these things, what should happen? This should be less than or equal to. This should prove what? Bottom. And also, they should fill up the space, right? Like if you have A and you join it with this thing, this should be greater or equal than true. So in a sense, it's something that fills up the space and it's inconsistent with A. In this case, yes. In this case, I could write equals, but I want to emphasize the important thing. The other, consider it like a bonus that you get for free. I can say even more. Yes, you can. You can say equals here and equals there, but then I would ask you, okay, which of the two is the essential here and the essential there, and then you would have this less than or equal to. Okay, so I'm out of time. Don't try not to ignore the homework. I'll try to force you to do that in some way that I will figure out. And we are pretty much done with. No, there is one more thing, not for today, but we have to see how exponentiation manifests itself in categories. And then we are done with categories, and we put everything together. That's the idea. Yes? The idea is what you mean by negation. So the way I'm using the word negation right here is only this thing, which I could describe it as the greatest element inconsistent with A. No, here I also need to say that they are the best somehow. Here I just said that they do what they have to do, and somehow it has to be the best. So we will sum these things up probably in the next lecture. See you soon, in a week.